All right, kiddies. Last time we talked about the atom. We talked about the electron shells. We said there were only so many electrons that could go in each shell. Those numbers again, I can put 2 electrons on the innermost shell. I can put 8 here. I can put 8 there. I can put 18. It keeps going, but there's only so many seats there. The inner shells are filled first because these are positively charged. The electrons are negatively charged. They are pulled down. They're attracted to the nucleus. But the big one here is that the atom really wants to have a full outer shell. The picture that you're looking at right now, there's this 1 electron out on the outer shell, and there are 17 empty seats there, and that just drives this atom crazy. So what it will do is it will make a deal. It will find another atom that wants 1 electron, and it will make a little deal. All right, there's 2 kinds of deals that go on. One is called ionic bonds. The other is covalent bonds. We'll talk about them both here, but that's where we're headed today, talking about bonding. The periodic table was the other thing that we looked at last time. We said that everything in a column has similar chemical properties because everything in this column has 1 electron in the outer shell. Everything in this column has 2 electrons in the outer shell. We said all of these were full. All these guys are missing 1 electron in the outer shell. These guys are missing 2, missing 3, and so on. So they all behave similarly. And we'll take another look at some of those details here. But let me tell you about ionic bonding. Right here is an example of ionic bonding. This is the atom sodium. And if you looked on the periodic table, you would see that sodium has an atomic number of 11. So that's 11 protons in the nucleus and 11 electrons that are arranged in these shells. So I put 1, 2 here. I got to get 9 more somewhere. This next shell holds 8. So the 2 on the inner shell, the 8 here would be 10. I've got 1 left over, and it's got to go in this outer shell. Not good for sodium. Over here, chlorine. Chlorine is number 17. So he puts 2 and 8. That makes 10. The 7 go here, and there's 1 empty seat right there. He's not happy. He's not happy. Nobody's happy in this case. So what sodium and chlorine do is they work out this little deal. And sodium says, "Psst, hey, buddy, come here. You, yeah, come here. You. And I got an electron. You want this electron?" And chlorine says, yeah, I'm looking for an electron. And so what sodium does is it lends the electron. It gives the electron. It lets chlorine borrow the electron, however you want to say that. They don't have brains, we don't think, so it's not a real thing like humans would talk and discuss, but this electron right there has a very comfortable place sitting right there in chlorine. So sodium and chlorine slip up next to each other. Sodium hands chlorine the electron, and that is a bond. What happens is sodium has 11 positive charges, and it just gave 1 away, so now it's only got 10 negative charges. 11 positives, 10 negatives. That means that it has a net positive charge. So sodium is now a positive ion. Meanwhile, chlorine over here had 17 positive protons in the nucleus. It just picked up the 18th electron, so it's got more negatives than positive. It has a net negative charge now. It is a negative ion, and this positive and this negative are attracted to each other. You can see the plus and the minus there. There's an attraction by that Coulombic force, like we talked about in test 2. Positives and negatives attract each other. So those are pulled together. They hold together in what we call an ionic bond. Ionic because both of these turn into ions when sodium gives chlorine its spare electron. When he gets rid of this electron, he thinks he's got a full outer shell. Chlorine picked up this guy. He thinks he's got a full outer shell, and everybody's happy. So that's an ionic bond. The other kind of bond is called a covalent bond. This has 3 different examples here on it. but it's all pretty much the same idea. In the first one here, you see that here's a hydrogen atom, and here's a second hydrogen atom. Hydrogen has 1 proton, 1 electron, so it looks like that. And you remember that that first shell holds 2 electrons. Hydrogen would really like to have 2 electrons. That would fulfill his outer shell needs there. So, but he's not going to, in the last case, atom A gave atom B 1 electron, right? If that happened here, then hydrogen would have no electrons, and he's not interested in that at all. That does not suit his needs. So what they do is they work out another kind of deal where the two slip up next to each other, and they share these 2 electrons. When hydrogen slips up next to hydrogen, then this electron from one atom, this electron from the other atom, they kind of orbit both electrons. They kind of go like this. Statistically, they spend more time in the middle because that way, if it were a really cold night, you could kind of build 2 campfires, right, and stand in the middle, get warm on both sides. In the same way, this positive and this positive tries to kind of hold on to both negatives kind of in the middle, but you can think about them kind of dancing around both of those, and that's a covalent bond. They have shared a pair right there. Those 2 electrons, one of them's from this atom, the other one's from this atom, but when they slip up next to each other, those 2 electrons participate fully in both atoms, and so it's a shared pair. Here's another example. O stands for oxygen, so I've got an oxygen atom, a second oxygen atom. Oxygen is number 8 on the periodic table. So he has 8 protons. That means 8 electrons. I start filling. I'd have 1, 2, 3, 4, 5, 6, 7, 8. That leaves 6 in the outer ring. He would like to have 8 there. He's missing 2 electrons. He would really like to have 2 more electrons. This guy would like to have 2 more electrons. So they pull the same stunt. They slide up next to each other, and this oxygen atom sends an electron over, and this one sends one over. Since they just kind of both picked up 1, this guy's got 7, that's got 7. Well, that's not enough. They both want 8. So this guy sends another one over, this one sends one over, and now they're sharing 2 pairs. This is what we call a double bond. Up here we had a single bond because there was a single shared pair. This is a double bond because there's 2 shared pairs. All right? But when you count the electrons in the outer shell, here's 1, 2, 3, 4, 5, 6, 7, 8 for this guy. And you count for the other guy, 1, 2, 3, 4, 5, 6, 7, 8. Everybody's happy. It brought everybody up to full time. So it's a good little deal that they work out here. And this is it's not like here's a house and here's a house and there's one kid over here and one kid over here. The 2 kids come play in the yard in between the 2 houses, and that way everybody's kind of happy. The moms get some peace and quiet. The kids get to play with each other. It just works out well for everybody. It's the same way here with atoms. Got one more example of covalent bonding. Here's a hydrogen, there's an oxygen, there's a hydrogen. And we already know that hydrogen wants 1 more. We know that oxygen wants 2 more. And we know that this hydrogen wants 1 more. So they work out a covalent bond deal. This guy comes and plays with oxygen. This guy comes and plays with hydrogen. So this one coming over here, that would make 2 in hydrogen. This one coming over here, that would add 1. So now he's got 7. Oxygen's still not happy, but the hydrogen's happy, so he's done. He's got this one and this one, we'll say. Up slips another hydrogen atom, and if they do the same thing, if this one comes over and that one goes over, there's a single bond right there. With this shared pair, it would look like this, like you see right there. And let's count the electrons for this hydrogen on the bottom. I've got 1, 2. He's happy. Hydrogen number 2 right here, 1, 2, he's happy. Counting the electrons for the oxygen atom, here goes 1, 2, 3, 4, 5, 6, 7, 8. He's got 8 in the outer shell, he's happy. All right, so that's a covalent bond. These things we just made right here, hydrogen, whenever we find hydrogen in nature, it's always H2. You just won't find a single hydrogen atom running around, because he's going to find somebody to make a deal with. Right here, oxygen, the oxygen that we breathe, is O2. It's two oxygen atoms tied together in this covalent bond. Right here, we just made water, right? You take two hydrogens and an oxygen, it combines and makes water. So that's those are all covalent bonds. On the last one, the one we had before, the ionic bond here, what did we make? Sodium and chlorine. That makes sodium chloride, which is table salt. So these atoms combine to make new stuff. If you played with Legos when you were a kid, you know you could take the red blocks and the yellow blocks and the wheels, and you go snap, 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 and you can make a car, you can make a boat, a spaceship, whatever. And you could make new stuff out of the building blocks. Atoms are the building blocks. Molecules are the things that we build with them. The sodium chloride and the water and the hydrogen molecule, whatever. All right. Now I wanted to go back to the periodic table real quick, because since the columns tell us how many electrons are in the outer shell, then, you know, when hydrogen and hydrogen make a covalent bond, then I could do other things that are similar. Better example, here, sodium right there and chlorine combine to make table salt. See how fluorine, right above chlorine, has the same number of electrons in the outer shell? So I could also take sodium and fluorine, and I could make an ionic bond there. I could take potassium and fluorine, or potassium and chlorine. Anything in this column will form an ionic bond with anything in this column. These guys all have 2 electrons in the outer shell. They don't like it. So what they do is they get together with somebody that wants 2 electrons. That would be these guys, this column. You can't see a whole lot of it, but there's oxygen. Down below that you've got sulfur, selenium, tellurium, and polonium. All right. So going down, you know, these guys will make an ionic bond with these guys, and it goes on and on like that. So if I'm pulling from one side of the periodic table and the other side, that's an ionic bond. These guys want to get rid of electrons. These guys want to pick them up. Ionic. Oxygen and oxygen make a covalent bond. Fluorine and fluorine would make a single covalent bond with each other, whereas oxygen and oxygen made a double bond. Nitrogen and nitrogen right here would make a triple bond. It would have 3 shared pairs. But that would be a chlorine. It would be a covalent bond. Right here, chlorine and fluorine. These two, they're both looking for 1 electron, so they could make a covalent bond with each other. And so anytime I'm pulling just off of the right-hand side, that's a covalent bond. Remember, though, that this last column, everybody there has a full outer shell, so they're not doing anything. They're not going to make any kind of bond with anybody because they are already satisfied. All right, here's a picture that kind of details what's happening here. When we talk about chemical reactions, it doesn't hurt to kind of draw the picture and to see what's going on. In this particular chemical reaction, we're mixing propane and oxygen. And maybe this is something you do all the time, right? If you go out in the backyard and you fire up a grill, you're taking propane, you're combining it with oxygen, and what happens is you cook your hamburger, but in the process you are turning propane and oxygen into carbon dioxide and water and heat and light. So this little picture shows the chemical reaction. Propane looks like this. It's C3H8. So C stands for carbon, and I've got 3 carbon atoms. H stands for hydrogen. I've got 8 of those. And you can see what it kind of looks like a little caterpillar thing here. 1, 2, 3. The black dots are carbon. The white dots, hydrogen. 1, 2, 3, 4, 5, 6, 7, 8 on the back there. So that's what propane would look like. Meanwhile, the oxygen, rather, we've already said that oxygen always has that covalent bond, so it's always O2. So here's 1, 2. That makes an oxygen molecule, O2. means take 2 oxygen atoms, tie them together into an oxygen molecule. However, I need 5 oxygen molecules. So here's 1, 2, 3, 4, 5 of them. If you count the molecules, you see there's 5. Each one's got 2 atoms. So clearly there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 oxygen atoms there. And the secret to this game is that I'm going to take some stuff and mix it up here. It's going to make some new bonds, but I have to end up with the same parts, the same pieces. When we were talking about Legos, you could take your Legos, snap them together and make a car. Then I could take all those pieces, take them apart and make a boat, but all the pieces still have to be there somewhere, right? There's pieces don't magically appear, and the pieces don't disappear. They all have to be there, at least on the floor, or somewhere. So if I take 3 carbons, 8 hydrogens, and 10 oxygens, then I better have 1, 2, 3 carbons, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 oxygens, and 1, 2, 3, 4, 5, 6, 7, 8 hydrogens on the other side. It has to balance, and that's what we call a balanced equation. I'm trying to get this heat and light, right, because that's what cooks my hamburger. But the propane and the oxygen combine, it makes carbon dioxide, which is a big thing in the news right now. I get some water out of it, and I get my heat and my light to cook my hamburger. This is the chemical equation right there. C3H8, that's 1 propane molecule plus 5 oxygen molecules. It gives me, see the yield there, yields, or gives, or equals, or whatever you want to call it. 3 carbon dioxide molecules, 1, 2, 3, plus 4 water molecules, 1, 2, 3, 4. And I get the heat. It's an exothermic reaction. It gives off heat. So that's the way of it. There is a lot that we can do here trying to balance these equations. I'll show you this one. We'll do some in class. Remind me if I don't get around to it. But a lot of times, this is like problem 2421 in the book. Here's H2S. Here's HNO3. Here's SNO3 and H2O. So what they're doing is they're saying, we want you to balance this equation. And the blue numbers aren't given. We're trying to find the blue numbers that make this work out. So with this example right here, then what you want to do is you start playing with it. All you can change are the blue numbers out front. And this one's already done. But if I come in here, I usually start looking for weird stuff like sulfur, right? I've got, before I put in blue numbers, there'd be 1 sulfur and 1 sulfur. So that would be fine. That would be balanced. But that would mean that I'd have 2 hydrogens here plus a 3rd one there. And only 2 there. So see how there's a problem with that? I got what did I say? 3 on this side and 2 on this side. That's not balanced. So I have to jiggle the numbers to make it work. Again, let's do some of those in class, because those are something you got to get your hands on and try. But you're kind of going back and forth trying to make the numbers work out right. All right. Thank you much.